Hi and Assalamualaikum. My name is Amran Najah. My matrix number is 229330, and today I will be presenting about solving engineering problems using dimensional analysis. So firstly, the introduction for this topic is engineers frequently involved in problems regarding flow of surfaces, such as shape of the wing of an airplane, or ones that involve chemical engineers, which are the trace of these silicon columns and surfaces of scrubber. By identifying the key parameters and applying the Buckingham-Pi theorem to obtain the dimensionless analysis, especially Reynolds number and comprehensive utilization of chemical processes, this study aids design upgrades in unit operation where surface and fluid interactions are crucial. So this is the variable used for flow of surfaces. There are 5 variables which are fluid velocity, length of surface, fluid density, dynamic viscosity, and drag force. So that will make it a total of 5 variables and the 3 dimensions used. So Buckingham-Pi theorem, what is it? Buckingham-Pi theorem is invented by Edgar Buckingham. It's a method used in dimensionless analysis to simplify a complex equation by reducing its number of variables, and it can be reduced by grouping the dimensionless variables called pi terms. So after we minus the number of variables and the dimension used, we have a total of 2 pi terms that needed to be found. So first is force. So this is the dimensionless analysis. And the final equation for this item is force over velocity, force over density, velocity squared, length squared. And this is the dimensional analysis for dynamic viscosity, which is pi equals to pi over density, velocity, length, which is the inverse of Reynolds number. So combining these two, we will make the final dimensionless relationship by using Buckingham-Pi theorem, which is force over density, velocity squared, length squared equals to F pi over density, velocity, length. So the engineering significance of dimensionless group is this dimensionless group was proven to simplify engineering to make more manageable calculating and analysis. By using dimensionless group, fluid flow behavior can be generalized disregarding its scale. In the chosen system, as an example, Reynolds number is used to condense governing equation until it's easier to solve and describe a fluid. Other than that, it also helps engineers in scale independency, where it facilitates the comparison of various systems independently of their scale. So for the real-world optimization challenge, one of the most vital challenges in engineers is some process like the construction of a ship hull that, based on the picture provided in the slide, requires a capital investment due to its large scale and complexity in its structure. However, these problems can be solved by utilizing the dimensionless group. To accomplish this, a smaller model can be built first and tested for its flow condition in order to reduce the cost of constructing the real ship hull model. So the flow condition of the model must match the real ship in order for it to function adequately. So this process will involve Reynolds number to simply match the turbulence and boundary of the ship and the model. After it is matched, the drag coefficient is applied to measure the drag of the model and predict the drag on the real ship. By doing so, they can economize the cost and the time in building an effective ship hull. So conclusion for this presentation, there are many uses of dimensionless group and its uses majorly in determining the flow onto surface. On the side, Buckingham-Pi theorem is applied to reduce the complex physical variable into two-dimensionless group to then calculate the flows and regimes simply. These include Reynolds number, drag coefficient, Mach number, and never-ending other dimensionless groups. The real-world optimization challenge also proved that dimensionless groups can be demonstrated their practical function in solving real-world problems, supportably the scale of model. That's all from me. Thank you.